Okay, this is the second lecture in Chapter 7 in Modern Chemistry. So we have been talking about the naming of compounds, and now we're going to look at some of the other characteristics of a formula for a particular compound and some of the other details about it. So the first characteristic is oxidation numbers. This is a number that is assigned to a compound or to an element within a compound that gives us kind of a general idea of where the electrons are likely to be located within that compound. This is not a number that's measured. It's not something that actually exists in nature that can be used for classification so much. It's in some cases totally arbitrary, but it gives us, it's more of a description of where electrons are likely to be based on what we know about the elements themselves. And it helps us to determine what kinds of elements will react with other elements, what kinds of formulas are likely to form when those elements react. And it has a lot to do with electronegativity. So you learned in Chapter 5 that electronegativity means that the element has a high attraction to or a strong pull on electrons. So if we look at this example here, this is what's called a hydroxide ion. So it's OH minus, there's an oxygen and there's a hydrogen, and together they have a collective charge of -1. Because the oxygen has an electronegativity of 3.5, the electrons are going to be pulled more closely toward the oxygen than they are to hydrogen, because hydrogen has an electronegativity of 2.1. So another way to think about this is in this image here. You see the electron cloud, and all of the electrons that are present here. We have oxygen's 6 valence electrons, and then there's a valence electron here from the hydrogen, and that those electrons are more likely to be found closer to the oxygen than to the hydrogen because of the electronegativity of the oxygen itself. So that's kind of represented here in the size of the electron cloud, showing that there's more electrons in the proximity of the oxygen than there are in the hydrogen. The use of the oxidation number, there are quite a few. Oh, so delightful. When I imported this, it lost all the numbers. So here's our first rule. There are kind of a few criteria or kind of straightforward rules when assigning oxidation numbers. Any element that is in its pure state or a completely, so let's say O2 or H2 for instance, it's just bonded to other atoms of itself. Both in that condition, all of the oxygen atoms in the O2 or all of the hydrogen atoms in the H2 have an oxidation number of 0. There's no likelihood that one of the oxygens will pull the electrons more strongly than the other because they're exactly the same. They have identical electronegativities, so they're going to share the electrons completely equally. When there's a compound that contains different elements, again, the more electronegative element will tend to pull more strongly on the electrons, and the oxidation number that it is assigned is equal to whatever the charge of the anion would be. So there are some examples here. So fluorine is a negatively charged ion. Fluorine always has an oxidation number of -1 because it is the most electronegative element on the periodic table, and it always is looking to gain one more electron to get up to the octet. Oxygen is in almost all cases a -2. Again, it's very high electronegativity. But when it bonds to fluorine, for instance, fluorine is the more electronegative element. And so oxygen in that case has a +2 oxidation number, which is interesting, but very uncommon. Hydrogen is generally a +1, has an oxidation number of +1, which is very similar to its ion. anytime it's with a more electronegative non-metal, which is most of the time. So for water, for instance, or CH4 is another one. Carbon is also a non-metal and it's more electronegative than hydrogen. So in both of those cases, hydrogen has a oxidation number of +1. When hydrogen is with metals, as we saw in the case of, let's see, we could do NaH, for example, sodium hydroxide, or sodium hydride, pardon me. The sodium has a charge of +1, so in that case hydrogen would have an oxidation number of -1. The important thing to remember about determining oxidation numbers within a compound is the sum of the parts, so all of the oxidation numbers for hydrogen plus the oxidation number for oxygen collectively have to add up to a sum total of 0, because all compounds are neutral. They have no charge. When we're dealing with polyatomic ions, the sum of the oxidation numbers is equal to the charge of the ion. So, for example, the hydroxide ion that we talked about earlier, oxygen has an oxidation number of -2, hydrogen has an oxidation number of +1, so -2 + 1 has an overall charge of -1, which is in fact the charge of the hydroxide ion. The usefulness of the oxidation numbers for formulas and names goes right along with the information that we learned in the last lecture, especially when dealing with things like nonmetals and some of the transition metals and the fact that they have multiple ion states. There are many nonmetals that also have multiple oxidation numbers. That just means that there are different versions of molecules or different versions of compounds that can form from the same two elements. So for example, here we have sulfate and sulfite. Actually, these aren't ions, so pardon me, that's going to be sulfur trioxide and sulfur dioxide. So we can use either one of the naming systems. We can use the stock system, which uses Roman numerals like this. So with our SO3, we would be dealing with sulfur 6 oxide and SO2, so this would be here, SO2 would be sulfur 4 oxide, or we can just stick to the stock system where we use, that is the stock system where we use Roman numerals, or we can stick to the prefix system, in which case these would be sulfur trioxide or sulfur dioxide. Another example here is with nitrogen oxide, and you'll notice that a lot of the non-metal compounds that have multiple versions have oxide as part of the compound. Oxygen forms so many different compounds so readily that it is often the second element involved. So we've got NO, which is nitrogen monoxide or nitrogen 1 oxide, just a couple of examples. The next characteristic that we're going to talk about is a little bit of review actually from, I think it was chapter 3 maybe, or chapter 4. So we've talked about the mass of an element, and we talked about it in terms of atomic mass in AMUs, or we talked about molar mass in grams per mole. There is another commonly used characteristic, which is formula mass. And the formula mass is just simply how much a larger compound or molecule or ion weighs. So this is for determining the mass of something that's not just a single element, but is a combination of elements. So for example, here we've got sodium chloride. And to determine formula mass, it's actually very, very easy. You just take the atomic mass of its parts. So the atomic mass of sodium is 22.99 AMUs. and the atomic mass of chlorine is 35.45 AMUs, and you add them together. So the formula mass for sodium chloride would be 58.44 AMUs. So we can use this in a similar way to find the molar mass of a compound or molecule or ion, just as I've done here with water. So with water, we've got that, again, this program does not like subscripts. So water has a total mass equal to its parts. The molar mass of hydrogen is the same as its atomic mass, right, 1.01, but since we're dealing with molar mass, it's grams per mole. And there are 2 hydrogens, so we have to remember to multiply by 2. And then the molar mass of oxygen is 14.01 grams per mole. So 1.01 times 2 plus 14.01 gives us a grand total of 18.02 grams per mole. So the formula mass of water is equal to its molar mass of 18.02 grams per mole. And we can use these values for converting, for determining if we know how much a certain sample weighs, we can figure out how many moles we have, or we can figure out the parts within that sample. And we're going to talk more about that in just a second. We can also describe a substance based on its percentage composition, or how much of each part is present in that compound. So we're going to stick with our water example, and it looks like my cute little equation got a little cockeyed over here. So the formula composition, or the percentage composition of water, let's say we wanted to know how much of any water molecule is made of oxygen. So we would take the mass of the oxygen, which is 16.00 grams, and we would take the total formula mass of water, which is 18.02 grams, right? We just saw that on the last one. And that's going to give us a decimal, which in this case is 0.8879. So to convert that decimal into percent, we multiply by 100, and that tells us that we have 88.79% of all water molecules is just oxygen. That's pretty significant considering there's only 1 oxygen compared to 2 hydrogens. You would, I think most people would kind of logically say, well, there are 3 elements, so each one is probably a third. But you can see oxygen's third actually makes up nearly 90% of the total molecule, which is interesting. So we can use all of these different characteristics and features about elements and the compounds that they form to describe the types of compounds that we are working with, or in some cases to describe the types of compounds if we've made a discovery. You're, mixing some chemicals in a lab and you end up creating something and you're not sure what it is. You can determine the formula of the compound by looking at what you do know about it, using what we know to determine what we don't know. And one way in which scientists describe compounds is empirical formula. So this means, what is the simplest version of a compound that those elements could form? A lot of times there are multiple versions of compounds, and sugar is a great example of this. So in biology, you probably learned all about glucose, which is kind of the body's basic sugar. There's also fructose, which is fruit sugar, and there's, all kinds of things. Let's say lactose, which is the sugar in milk. The thing that's interesting about all of those sugars is they have exactly the same empirical formula, which is C1H2O1. So it says that in every sugar, there's 1 carbon for every 2 hydrogens and every 1 oxygen. And that formula never changes. What does change, that ratio within the formula doesn't change. So the ratio is constant. But what can change is the exact numbers within the compound itself. So for instance, glucose happens to have 6 carbons, which means it has 12 hydrogens and 6 oxygens. But fructose is different. I don't remember off the top of my head how many of everything fructose has. It might be 7 or 8. Lactose is slightly different. But the formula, the ratio CH2O, is constant. So a lot of times we will use these empirical formulas to describe whole types of molecules, hydrocarbons or fuel like butane, propane, things like that. They also have the same empirical formula. It's just different numbers of elements within the formula that changes. So we can determine the empirical formula by using percentage composition. If we know how much of a certain element we have, we can determine its percentage, and we can then use that percentage to find the mass of each element present. So we can work from a percentage to find the formula. We can work from the formula to find the percentage. There's a few different ways that we can convert here, and I'm going to show you an example right now. So here is an example of using percentage composition in order to determine empirical formula. So the way that we're going to do this is we say we have this compound and all we know about it are the percentage of elements present. So we are going to assume that this compound weighs 100 grams. It doesn't really matter, but it's an easy number to work with. And we're going to say if the total compound is 100 grams and 32% of it is sodium. Let's convert that to a decimal. So 3.3238 sodium. That tells us that we have 32.38 grams of sodium present, and we have 22.65 grams of sulfur, and finally 44.99 grams of oxygen. Right? So out of a 100 gram sample, this is how many grams each of its parts would make up. So then from there, let's figure out how many moles of each part we have. So sodium equals 32.38 grams. And sodium's molar mass is 22.99 grams per mole. And then I'm going to scoot this up a little bit. And we have sulfur, which is 22.65 grams. And sulfur's molar mass is 32.06 grams per mole. And finally, oxygen, 44.99 grams. Times a molar mass, scoot a bit more, of 16.0 grams per mole. Okay, so when we do the math here, we find out that we have 1.408 moles of sodium, 0.7065 moles of sulfur, and 2.810 moles of oxygen. So what that would tell us is if we were going to make a formula, a chemical formula from this, we would have sodium 1.408, sulfur 0.7065, oxygen 2.812. You know that chemical formulas can't look like that, right? Chemical formulas never have decimals. They're always in whole numbers. So clearly there's something off with this formula. We've done all of our math correctly. So what we can do now is use this formula, these ratios of moles, and convert them into whole numbers. So the way that you do that is you look at your mole numbers and you find the smallest one, which in this case is sulfur. You divide each one of the other mole numbers by the smallest number of moles present. And what that will do is it will give you a whole number ratio between your moles. Occasionally these numbers will come out just slightly above a whole number or slightly below, but most of the time they're going to come out pretty darn close to what you want. So what we're going to get here is 1.993, which is awfully close to 2. This, of course, will work out to 1. And then our last one is going to give us 3.980, which is awfully close to 4. So now we've got our ratios into whole numbers, and we can use that to make a chemical formula that has whole numbers. So instead of 1.48, 0.7065, etc., we now instead have sodium 2, 1 sulfur, and 4 oxygens, Na2SO4, which is in fact a compound called sodium sulfate. So that's just one example of how we can use percent composition to tell us the formula of an unknown compound, and we'll do a lot more of these examples. Okay, so the last part of this set of notes is using just a different characteristic. Instead of using percent composition, we can use the total mass of a compound and the empirical formula of that compound to determine the actual molecular formula. So remember, the empirical formula is the simplest version of a compound. The molecular formula is the specific version that we're looking at. So in this case, we have an empirical formula, which is C1H1 or CH, and we have a mass, and we want to know what the specific compound that we're working with is here. What's the actual formula for the particular compound that has a mass of 78.110 AMUs. So the first thing we want to do is look at the formula mass for our empirical formula. So the formula mass for CH is going to be the mass of carbon, which is 12.01 AMUs, plus the mass of hydrogen, 1.01 AMUs, for a total of 13.02 AMUs. And then we're going to use the mass that we're given. So our given mass is 78.110, and we're going to divide it by our formula mass, which is right here, 13.02 AMUs. And that gives us a value of 5.999, which tells us that our specific chemical formula here is 6 times, so our specific is 6 times greater than our empirical formula, which means, right, if you think about it as 6 times greater than the empirical, if we do that multiplication and distribute it just like you would in algebra, we have C6H6. So the specific compound that has a formula mass of 78.110 and an empirical formula of C1H1 would be this compound, C6H6. I hope that makes sense. So we're at the end of our lecture here. There are so many sample and practice problems scattered throughout all of Chapter 7. I would really encourage you to do a couple of those so that you can come in and ask questions about the parts that you are struggling with or that you're getting stuck on somewhere, and we can work on those in class. And I will see you soon.